All right. So here we go. Here we go. Let's have some fun today. So today we're going to be talking about AI hardness and AI completeness.
Woohoo!
So to inspire what we will talk about, I'm going to start by asking you guys some questions, and you can see one question right here. And when you see a question, I want you to raise your hand if you think that you know the answer to it. It could be a complete guess, even if you're a little bit unsure, but if you think you have the ability to answer the question, you should raise your hand. And I will pick on someone, and if you get it wrong, it is completely okay. But I want you guys everyone to participate and be aware of how many people are raising their hand and who's raising their hand. So first question, what is the verb in this sentence? The knowledgeable teacher gestured towards the board. So who thinks they know the answer to this question? Okay, Yongjin, what's the answer to this question?
Gesture.
Gesture. Does anyone disagree? Okay, so nearly everyone thought they knew the answer to this question, and indeed, we did find the correct answer. Here's question 2. What is the best chess move for black in this position? So if you think you have the capability of answering this question, which should be anyone who kind of knows how chess works, raise your hand. Again, you don't need to necessarily know the best move, but you should have your idea of what the best move is. We'll give another second to ponder it. Guess no one here is Magnus Carlsen yet. Okay, so who thinks they know what the best move is for black in this position? Okay, substantially less hands. Ian.
Bishop to, what is that, B1, maybe?
Bishop B1?
I don't know.
Okay. AJ?
This is a guess, but rook 1 to the right. I can't read the letters.
This one?
No, the other rook.
Oh, this one here.
Yeah.
Okay. Okay. Rook to E8. Rune?
I'm gonna guess knight
Knight E4. Centralizing the knight. Any other guesses? Okay, AJ, another guess?
Well, I think if we're thinking like AI.
No, we're not. We're not.
Pawn to B2.
Pawn to B2.
Wait.
Oh, pawn to...
Wait.
But that is
Pawn to
AI,
G2.
though.
No, pawn to G1. I don't know how
Huh?
to this number.
No, that's not possible,
pawn?
bro.
Yeah.
Yo.
Just
Here?
take the king.
Okay. No, we're still playing by chess rules. Okay, so at moderate depth, the best move in this position is indeed bishop takes b1. It's a nice thing. So we saw with this question, substantially less hands, but we still solved it. Question 3. What animal is in this picture? Veda, what animal is in this picture?
Cat.
Cat. Anyone disagree? Robbie?
Really large rat.
I was spent 2 minutes trying to find a cat picture like this. Okay, so again, nearly everyone had their hands up and found we had the answer to this. Good. Question 4. What is the product of these two numbers? I'll give you 10 seconds. Should be enough. Hey, no cheating, no cheating. Yeah, I see that. No cheating.
I'm using my resources.
It's a tool call.
Yeah.
Okay, who knows the answer? AJ?
38.
Okay. No. If I gave you maybe an hour, do you think somebody in here could solve this problem? Yeah, so you all could probably solve this question just given it enough time. All right, sounds good. And I think this is the last one. Translate the following sentence to English. Anoche, dormí 5 horas. All right.
Yesterday night I slept 5 hours.
Great. So about half the hands are up. Anyone disagree? No. Okay. Cool. And we got the correct answer. So okay. Thus far, all you need to observe is that most of these questions, as a collective, we solved. Some of these problems, all of us knew the answer to pretty much instantly. Some of them we didn't know the answer to individually, but other people in this room knew the answer to. That's all you need to think about right now. This is just to inspire what will come down there. Here's one more actually. Perfectly predict the open price for Google, the stock Google, for the next 5 business days. So who can do this? Keyword here being perfectly. Yeah, I thought so. So now we have a problem, unlike the previous 5, where nobody can do it. Like, at all. Like, none of you will ever predict for the next 5 business days. And even if you do get super lucky, let me just change this question to the next 100 business days. Right? And none of you will, ever solve that. So this question is different from the first 5, in a sense. Okay? Still a little abstract, but we live with it. So, before we progress into some of the newer content, let's do a quick throwback to lecture 1, and also a throwback to your quiz, because this was part of your quiz. So we learned lecture 1 that there are these 2 types of problems. There are decision problems where you say yes or no to every input, and there are these optimization problems, where you try to optimize something. And if we're being real, the union of these 2 classes, like optimization problems and decision problems, don't really solve every single problem. Like, for example, perfectly predict the open price for Google for the next 5 business days. This is a problem in the sense that you have a problem statement, but it's neither a decision problem nor an optimization problem. So if that's the case, we spent the entire semester studying these 2, which is fantastic, right? There's tons of problems in both of these. But now when we start thinking about advanced technology and AI, we want technologies that can solve problems that fall outside of these 2 classes, perhaps. Now I'm quickly scanning my lecture notes to see what nonsense I wrote down. Okay, we'll talk about that in a moment. And then also in lecture 1, we said, okay, if we have decision problems and optimization problems, we can further stratify them into easy problems and difficult problems. And easy problems, we defined it by computational complexity. We said easy problems were those you could solve quickly or in polynomial time. And we said difficult problems were pretty much everything else. Right? This was our definition from way back when. So hopefully this is still in memory. So, as I just said, these decision problems and optimization problems don't necessarily encompass all problems, such as playing chess at an elite level, right? We have computers that can play chess better than any human, but this isn't quite like a decision or optimization problem. Maybe at a granular level, each step is optimization. That's besides the point. Or finding the verb in a sentence on its own, it's not a decision problem. It's not really an optimization problem. But you can imagine us desiring technology to be able to solve these problems. So when we do this, we're expanding our horizons to many, many more problems. When we do this, our original classification of decision and optimization and easy and hard starts to fall apart because not all of these problems fit in those classes. So today, we will try to expand our horizons to more problems and try to develop some sort of organization that can help stratify these problems into different classes, and that perhaps give us some interesting conclusions. But we'll see. Any questions thus far? So here we go. We'll try to classify said problems, but when we think about the problems we just saw on the first two slides, to us, when we were solving those problems, some of those problems were a lot easier than others, right? The first question, identify the verb in the sentence, everyone had their hand up, and you all solved that instantly. Whereas playing chess at an elite level, or finding the best move in that position, I gave you more time to think about that one, and only a few people had their hand up. And even then, we didn't all have the correct answer to that. So, semantically to us, these two problems are quite difficult, or quite different in terms of difficulty. And then when we go to the perfectly predicting the stock market, well, that's nearly impossible, right? I can study the chess position for as long as I want, and I can probably eventually deduce the solution. I will never, ever be able to perfectly predict the stock market. So what this is trying to do here is you should be sensing we have this difficulty differential between different problems, just as we did when we were talking about normal complexity, where sorting a list is much easier than finding a satisfying assignment to a Boolean formula. We said those were of different difficulty, and we thus put them in different classes. This is what we're going to start to do. We sense a difference in difficulty here. We're going to try to compartmentalize that. Difference in difficulty. Say that 5 times fast.
Difference in difficulty. Difference in difficulty.
Fast. I said fast. That's not fast.
Sorry.
Faster. Go.
Difference in difficulty. Difference in difficulty. Difference in difficulty.
But you're putting too much of a pause in between.
I am. I'm
Fast. Fine.
sorry.
Practice.
This is a difficult problem.
It is a difficult problem saying it 5 times fast. Okay. Any clarifications needed thus far? Okay.
Wait, real quick.
Yes.
Why is why is the Google stock prediction not an optimization problem? If you think about it as your objective is to get as close as possible to the true price and finding an optimal predictor.
Sure. We could rewrite it to make it seem more optimization, predict for each day to minimize the difference. However, maybe an argument there is perfectly predicting we want 0 difference. And also we will still consider optimization problems right now. We're going to consider decision problems, optimization problems, and more. So we'll still consider optimization problems. If you want to view this as optimization, sure. Okay, go ahead. Yeah. Anything else? Very well. So, slight detour, but still very relevant. We're clearly living in a world of AI, and we're in this AI race to obtain something called AGI. And maybe you've heard of AGI, maybe you haven't. We'll talk more about AGI in 10 seconds, but it feels like every single day some sort of new tool and technology is coming out that's changing the landscape of AI. Google has been going on an absolute rampage this week. Oh my goodness. Gemini 3 launched a couple of days ago. There's some new nano banana thing coming out, or maybe it already came out, and that looks absurd. They released anti-gravity, which I think is a competitor to Cursor. Google's an absolute menace, right now. And then you still have these other, very big name companies, OpenAI and Anthropic, who have their own models, and they're also absolutely fantastic. And you see that every couple of months, something new comes out, and one of them suddenly becomes the king of the hill. But they're all kind of trying to race to achieve this trophy of AGI, or artificial general intelligence. So we'll quickly define what AGI is, and we'll talk about it throughout today. So in very simplistic terms, for the purpose of this lecture, our definition of AGI is going to be that, well, we will say that an AI, or a technology, exhibits AGI, or artificial general intelligence, if it can do any task a human can do. And so there might be a little hesitancy in reading this definition. We're just going to accept this for the purpose of this lecture, that a technology is an AGI if it can perform the same tasks a human can do, or to the same level as. That's just what we'll accept as the definition. So keep this in mind. We'll use this throughout today. And in fact, we're going to try to not solve AGI, but we're going to try to make AGI more accessible. If you think about it right now, like, what does it mean to obtain AGI? Well, to create something that can do any task a human can do. That's a lot of stuff. That is a lot of stuff we're expecting out of our single technology right here. At this point, it seems, I don't want to say infeasible, but think about everything a human can do. There's millions, if not billions or trillions of things. And we're expecting this out of our technology. Hopefully, by the end of today, we'll see, maybe it's not so bad. I mean, it's still bad, but it won't be as bad. Maybe. Probably.
Bad for who? Bad for the humans or bad for the company?
Bad for the developers who are trying to obtain AGI.
Oh.
Right? If you're a developer trying to create something that can do everything a human can do, that's a lot of stuff. That's pretty bad. That seems like a lot of hard work. So bad from the developer perspective. Good question. Okay. So, in the quest for AGI, darn. Well, before we go further, we're going to define a useful tool. And this is going to inspire a lot of the work that we do going forward. We'll call this a human oracle, or an HO. So a human oracle is a function that takes as input some sort of string, which input doesn't really matter. But the inner workings of this function is you have all humans collectively together. So you put all humans in a room, you give them some input, some sort of question, and the humans are allowed to look at that question. They can collaborate with one another if they want, but they're going to output the answer to the question, right? So if I have all humans in a room and my string input is what is the verb in the sentence the teacher gestured at the board, all 8 billion humans, look at that question, collaborate with one another, and then they ideally output gesture. And we will also give the humans the access to a very basic Turing machine. And this Turing machine, it's just a very simple computer. Maybe it does some data processing with the input. Maybe it can code up some simple algorithms. But this is there should they need it. So human oracle is just all humans collectively working together, maybe collaborating. They get some sort of problem or some sort of input. They have to give the answer or output. Yeah.
Does it have all memory of human history and knowledge and all that too, or is it just? Do we only assume that individual actors are working on this, right?
We are taking all 8 billion people currently alive in their current state with their current brains and putting them in.
Sure.
So whatever you can bring to the party.
But that includes using current tools that we have as well to solve these problems.
We will use the tools you have are your brain, everyone else's brain, and simple Turing machine.
Okay.
Is it when is there a time limit for the processing? And two, is it like I guess the resources are kind of important in this question because like it, you could just say, oh, if there's a bunch of humans invented everything already. Did they just invent everything again and they have access to everything? Like what does it mean if it's just humans?
Yeah, let me see if okay. So there is a lot of nuance to this. This is just kind of a glorified way of saying humans can solve the problem. So the problems we saw, like the questions we saw very early on, like what's the best chess move, what's the verb in the sentence, questions like that. This function is saying, can the collective of human minds solve that question? So with the chess question, in this collection of humans, we have Magnus Carlsen, who is like, we have Magnus Carlsen right there, who looks at the position. We'll give him, maybe an hour or something. He's going to find the best move. We're not going to really take time into account here. So some of these problems might take a long time. This is a function that asks, can humans solve the question? I know it's a little uneasy, but is a problem human solvable?
So like no one knows as of now what problems human can't solve. Like no one knows that for a fact.
Well,
Like tomorrow, another problem can be
correct. Let's just say at this point in time, right now, we collect everyone
sure.
and we give them the perfectly predict the stock market for the next 100 days. That's not human solvable.
Yeah.
No one's going to. Okay? So this is our human oracle. This represents all humans at the current point in time with their current brains sitting together, receiving a problem, and potentially giving an answer. So we say that a problem is human oracle solvable if on an input M or given a question, the union of human minds plus access to the basic Turing machine, which honestly we don't really need to worry about this too much, but whatever, if they can solve the problem. That's what it means to be human oracle solvable for a problem. And an equivalent definition is that if a problem is human oracle solvable, we will call it an AI problem. So henceforth, I'm going to be using the term AI problem. So whenever I say something is an AI problem, that means that problem is solvable by this human oracle, that the collection of human minds can solve the problem. So for example, finding the verb in the sentence, finding the best move in the chess position, what animals in the picture, things like that. Other questions while I buy time and read my notes? My notes are completely wrong anyway, so no. Anything? Okay. What's everyone's favorite AI tool? Really? Come on.
Clippy from Microsoft Word.
Yeah.
Little paperclip. He's a chiller.
He probably won't kill us.
Not yet.
I feel like you can say what you want, but GPT will always be the day one.
I know. As much as I hate GPT, I keep coming back to it. It's like a first love. Okay. We have our human oracle, right? We know what an AI problem is. So here we go. Here are some examples of AI problems. Identifying a cat in a photo. Translating sentences from Spanish to English. Driving a car. Writing Python codes. Gossiping. These are all things that can be described as problems, and the human collective, we can do it together. These are some examples of AI problems. Okay. Let's draw some, start to draw some parallels. So remember our definition of AGI a few slides ago. We said that we will say that an AI exhibits AGI if it can do any task a human can do. And we've defined AI problems to be the problems that the human that is human oracle solvable, or that the collections of humans can do. So to add a little bit more formality, we're going to be saying that we should expect any valid AGI to solve any AI problem by definition. So you just take two definitions together and mush them together. So AGI needs to be able to solve any AI problem. Very well. I am on this page. So what? Right? At this point, it's just definitions. We're still in the quest for AGI. Now, instead of saying AGI should do anything a human is capable of doing, now our definition is that AGI must solve every single AI problem. All right, that's great. Still, the question is, like, how do we know if we have AGI? And, like, it's still a daunting task solving every single AI problem because there's billions and trillions of them. So, like, what's the point of all of this? And the point of all of this is to give structure to define some classes of problems. So we're gonna draw some parallels here, and we'll do some throwbacks to complexity. So when you learn about complexity, the types of problems that we think about are NP problems, these non-deterministic polynomial problems. And some examples of these problems are, is 37 prime? This is a decision problem, right? We know that, like, either you say yes or no. Is 37 prime? Yeah, I should have put 91. Okay, that's that. Is phi satisfiable? Given a Boolean formula, is it satisfiable? We spent 12 weeks talking about this problem. Is there a path from S to T in a graph? Decision problem, again. So all of these we said were NP problems. This is like kind of what you learn in 262, or what's 2620 now. And then from there we say, like, okay, some of these problems have similar vibes to one another, whereas other ones are a little bit different, right? Like, is 37 prime is pretty darn easy, and is there a path from S to T is also pretty darn easy, but is phi satisfiable is pretty darn hard. So we begin to, like, stratify them and create these classes, and as you are experts in by now, we have easy problems, we have hard problems. So throw back to lecture 1, throw back to the start of this lecture. We compartmentalize these NP problems into easy and hard. We said easy problems were those that were polynomial time solvable, which created the class P. We said everything else is in a hard problem, not P, which is not the same thing as NP. It's just everything that's not NP. And we get this these two kind of classes. And then further, we said, you know, in this set of these hard problems, there's this special class of problems called NP-complete problems. And you do the proof showing that, like, okay, all these NP-complete problems are equivalent to one another, and they're considered to be the hardest NP problems. And we learned this thing that, like, if we can solve a single NP-complete problem quickly, then we solve any NP problem quickly, right? This is the whole notion of, like, P versus NP, solving something in polynomial time, showing things reduce to one another. That's why we have these classes. The reductions show equivalencies in a complexity sense. And then the whole, like, the whole race is, can we solve an NP-complete problem as quickly as possible? If so, we have that. Right? This is what we learned in 2016. Right? Need any more refreshers on this? Great. So we're going to take this as inspiration, because before we had NP problems, we've just defined something called AI problems. We're going to see what happens if, like, I kind of take this but do it for AI problems. So here we go. Well, before that, here's another visualization of it. This you may have seen. So, like, this is our class of NP problems. These are our easy questions. Everything outside is the hard questions. Special set of very hard NP problems. Then you have NP hard problems, which are at least as hard as anything in NP. Right? That's kind of the visualization that we see. And so let's begin to draw a parallel. We're going to try to create a similar diagram for AI problems. And it's going to be very, very simple. This is our definition of what it means to be not what it means to be NP complete, but NP complete gives us this fact that if we can solve a single NP complete problem quickly, we can solve any NP problem quickly. So let's see what happens if we get rid of the word quickly, because time is kind of weird in the AI sense, but whatever. And then let's just change NP complete to AI complete and NP problem to AI problem. Right? Just some small substitutions. And I know we haven't defined what AI complete is, but suppose we do. Right? Suppose we do that. We know what an AI problem is. Suppose we have this class AI complete, which parallels what NP complete is. If we are able to accomplish this, and we are left with this statement that if we can solve a single AI complete problem, then we can solve any problem, this would be pretty good news. Because remember, AGI, the quest is to solve any AI problem. And so if we can make this magic happen, then the problem of having AGI, of solving any AI problem, comes down to, can we just solve a single AI complete problem? So we've just taken NP stuff and just changed a couple of words to AI. And if we do this, all we need to do is define these classes in a way that parallels complexity, or NP, and ideally we will reach this conclusion, and that makes the task of getting AGI a little bit more digestible, because then we just need to solve one problem.
If we take out quickly, then what's the point?
Kind of what I was saying to Varun, that it's not that we're ignoring time, because time is important, but the focus now is can the collection of human minds, do they have the ability to solve the question? So when you think about it from a complexity standpoint, where we're kind of thinking through the lens of computers, a lot of these questions, like the satisfiability problem, we know that a computer can solve it. It can solve it if we give it a ton of time, right? So there we classify, or our stratification of easy and hard is defined by time. With these problems, we're defining the stratification based off of humans' abilities. So some problems we don't know if humans can solve or not. So it's not to say that humans will have unlimited time, but it's just if we take all human minds in their current form, can they deduce the solution to the problem? And I hope with the Google stock market thing, you'd agree, no matter how much time I give you, it's never human solved.
So it's more about simply if the problem can be solved than any notion of is the AI doing it better?
Correct. For AGI, we wanted to do anything a human can do. So can it complete the task? So not necessarily better than humans.
If it took it 50 years to figure out how to plumb a toilet, that is correct in a sense, even though it would never outpace anything that a human could do.
By our current definitions, yes. We can begin to change things up a little bit. Maybe you can change the question to plumb a toilet in 5 minutes. That's human oracle solvable. Maybe maybe our AGI can do it, but not in 5 minutes. So then we're getting into the weeds a little bit. So for now, it's just kind of let time be.
Got it.
So you'd say all AI problems are less harder, at least as hard as AI problems.
Say that again?
So all AI problems are less harder, as hard as AI complete problems.
AI complete problems, we'll define it in just a minute. but we're going to say that AI complete problems are the hardest of the set of AI problems, just as NP complete were the hardest of it. Great questions. Other questions? Coolio. Here we go. And yeah, if we do get this statement eventually, this means like we have HEI if we can solve a simple AI complete problem. And so our goal now is to define the class AI complete, and then ideally we solve a problem from that class to obtain HEI. We're not going to solve the problem because, spoiler alert, I don't have HEI for you today. Maybe tomorrow, but not today. But like the race is to solve a single problem from AI. Let's define it. So, this is the visual that we just saw for complexity now in AI world. So we have this class of AI problems, which we defined earlier, human oracle solvable. We will ideally break them up into AI easy problems, the easy problems. So AI easy parallels P, and hard problems, which are not AI easy, which parallels not P. We'll have this subset of AI complete problems, which parallels NP complete. And ideally, with our definitions, we will define everything in a way where we can say, if we solve a single AI complete problem, then we can solve any AI problem, right? It's the same diagram, just now in terms of AI. So here we go. Diagram, same diagram from before, just now with AI in it, right? There should be a little circle down here that says AI easy, but we don't really care about AI easy right now. But same diagram, essentially. So here we go. We're going to define these classes. We'll start with AI easy, because this one doesn't really matter, right? Like, we don't really care about P. It's like, cool, P exists, but not interesting problems. Same thing with AI easy. And like I said, we're going to define it in a way that it parallels the complexity class P. So here, this is kind of the definition, and I don't like this definition, but I know you will have questions about it. I'm just going to say, don't worry about it because it doesn't matter. A problem is defined to be AI easy if the problem is solvable in polynomial time by a standard Turing machine. So yeah, now we're introducing time all of a sudden, but still I'm going to say, don't worry about the time. There's a reason it's in quotation marks. And the simpler definition of AI easy is problems that are conceptually simple for computers, which you might argue is a worse definition, because what does it mean for a problem to be conceptually simple? But I argue it's a better definition, and we don't really care about AI easy problems. Robbie, I'll get to your question in just a moment. Let me give you some examples of AI easy problems. Again, this is meant to mirror P. So spam filtering, when it comes to emails, saying if something's spam or not. Route planning, finding the shortest path between two things. OCR, which is optical character recognition. Given a PDF, can you tell me, can you give me the text of the PDF, maybe as like a TXT file, something like that. Playing tic-tac-toe, multiplying two 50-digit numbers, or some basic chess. So all of these problems, from a complexity lens, they have different time complexities. Some of these are the polynomial, or maybe not polynomial, but the polynomial describing the runtimes is going to be different, but they are conceptually simple for a computer. I don't quite want to say that they're in P, but it parallels the class P. They are easy for computers, just as problems in P were easy for us humans. Robbie.
What does it mean to solve one of these problems? Because obviously OCR is not going to be totally accurate. So how do we know if we solved it, or
Who's we?
I don't know, how, you say OCR is an example of an AI easy problem, but it's never going to be 100% accurate. So how do we know that it's actually solved it versus
So we'll define the OCR problem to be, given a PDF, provide me the text in a TXT file such that it's completely correct.
Yeah, but we haven't invented completely correct OCR, right?
Maybe not, but does that matter right now?
Well, then how do we know it's AI easy?
So it is, we'll say it's conceptually simple, and maybe we'll just say the PDF is simple text. And there, I'm pretty sure we have some top tier OCR algorithms that are pretty much 100% correct. But it's still an AI problem, and it's conceptually easy for a computer. Other questions on AI easy? I don't want you to get hung up on this because this class does not matter at all. Not class like 1921, like this class AI easy, it doesn't matter. Oh yeah, of course we're gonna no, I'm just kidding. Go for it.
I just like read a, or I heard of a paper a while back saying like, oh, AI is like, at least the models that they're currently there are like, oh, that they're Turing complete. So, and then you just define it as like, what, like, is AI easy if it can be solved by a Turing machine? So wouldn't that guarantee AI can already solve all easy problems? I to be honest, I haven't read the paper that well. This is just like what I've briefly read from the abstract.
I don't want to give you wrong information, so I'm not going to answer that question, unfortunately. It's a great question. If you can send me the paper, I'd love to read it. But yes, yeah.
So when we count like AI, we're counting like an ensemble of like, you know, normal computers with, you know, vision models and, you know, large language models in like one thing.
Let's say an AI is a piece of technology, and however the inner workings work is up to the technology. There's like no human involved, like there's no human mind there, and it's not consulting a human mind. And we just give the AI a question, and it gives us an output. Okay. So the inner workings, whatever. It's just some sort of technology that can do this. All right, move on from AI easy. Good question, guys. I know I teased you, Varun, but I'm just messing around. So yeah, remember, AI easy is a subset of AI problems. And so all of these problems are human oracle solved. So the collection of human minds together, like we can solve all of these problems, right? We can take a PDF and read it and give you the text from it. And we can multiply to 50-digit numbers. It'll take some time, but it's in humans' abilities. All right, here we go. Time for AI complete. So we'll borrow the definition for NP complete. And the definition of NP complete is exactly this. So problem Q is defined to be NP complete if condition 1, Q is in the set of NP problems, and 2, every other NP complete problem Y is polynomial time reducible to Q. This is exactly the definition you learned from 2620. There you go. That's what it means to be NP complete. Let's just go ahead and change a couple of words. Right? A problem Q is defined to be AI complete if Q is in the set of AI problems, and any other AI complete problem Y is polynomial time reducible to Q. This is going to be our definition of AI complete. We'll live with the definition, and we're going to define this stuff and hopefully show that the properties we behaved in NP world, the complexity world, are also mirrored in AI world. That kind of like the reduction stuff is still possible, and we have the equivalence thing. But this is just going to be our definition. Again, identical to NP complete, just we change some of the words.
So I guess the top one is saying any NP complete problem can be reduced to any other NP complete problem, right?
Yeah.
Can any NP problem be reduced to any NP complete problem?
Yeah. Yeah.
And the other way is not true.
I think so. I always get the directions confused, but yes, NP complete is the hardest in that set. And so the reduction's good. We'll see, we'll draw it out in a little bit too. But okay. Anything else? Alright. And so like this second criteria here that any other AI complete problem Y is polynomial time reducible to Q, should we live by this definition, this gives us the equivalence that we enjoyed in complexity world, where NP complete problems we said were equivalent to one another, and so they were all the same, and if you solved one, you solved any of the other ones. If we subscribe to this definition, then we'll enjoy the same equivalence, that a single AI complete problem is the same as all of the others, hundreds. And so what this tells us is that under this definition, if we show like these definitions hold and we have these classes, then what we can do, if all of this is true, is solve a single AI complete problem, which by definition of NP complete means that we have solved all AI complete problems, which by the first part of the definition of AI complete and the second one means we have solved all AI problems, which means we have AGI. So the hope is to show this class structure, and if it all holds, AGI boils down to solving a single AI complete problem, which seems a little bit more manageable.
Do we have an AI hard problem?
We will define AI hard in a couple moments, but yes. Other questions? So here are some examples of AI complete problems. Full natural language understanding. So as an example, when given this sentence, the trophy doesn't fit in the suitcase because it is too big. If I ask you, what does the word it refer to in the sentence? What's the answer to that question? The trophy, right? And so almost all humans can solve that pretty simply. But in the early stages of developing technologies that tried to understand natural language, these types of problems were very confusing for them, and they failed on this a lot for some of the basic NLU technologies.
Does this also include problems that are like motion based? Yes. So like a human can move a glass. So does that also?
Yes, that is also an AI complete problem,
Okay.
like physics understanding.
But like I'm just asking, is the AI required to actually like do physical movements, or is it more just like kind of screen based tasks?
By physical movements, you mean like play soccer or something like that?
Yeah.
Or like make a build.
Like kind of like I feel like it's hard. Like AI can do a lot of like computer based things,
Mhm.
and like, but it's not really good at robotics. For example.
Right,
So is
right.
that part of it?
The answer with very high probability is yes. The reasoning why is not something I can think about in this moment, because I would want to prove to you why that's the case, but I can't come up with the proof right now. But we'll say the answer to the question is yes.
Because I guess a human could do it.
Right. It's human oracle solvable, I suppose. AJ.
If like within NP, oftentimes we're like justifying that something's like NP complete because it reduces to something like CNF sat. Like I feel like CNF sat like for like pretty much half the reductions we did in 262, for example, that was what we were reducing to. With like AI complete problems, do you think there's an analog to like CNF sat in which there's like one problem where like all of these different things are most easily represented as?
So Ian just asked a question about AI hard questions, AI hard problems. And I said we're going to see that in a few minutes. We will see the answer to your question after we answer Ian's question. Okay? So both of you are in the queue right now. You guys are just predicting my slide deck, which, come on, where's the surprise? No, this is great. You're thinking about it hard. Yes, but AJ, I will warn you right now. We're going to perform a reduction, and you're going to hate the reduction. All of you are going to hate the reduction. You're going to be like, what in the world did we just do? Like, this is fake. This is like not real. I'm warning you right now. It's abhorrent. It's terrible. But another disclaimer, this theory of like AI hardness, AI completeness, is very like weakly defined. There are a handful of papers out there. Most of them were from the 90s. And like some of their definitions of AI hard, let me see if I have it in my notes here. Like it is some of the worst definitions of all time. They were basically saying that like a problem is AI hard if it satisfies some sort of probability and if a bunch of other people think that it's a hard question. So a lot of this is based off of a single paper, which I'll share the paper with you guys. I found it kind of confusing, a lot of the wording. And so the reduction we'll see is inspired by some of that, and it's very unsatisfying. Pun somewhat intended. So that's just the disclaimer. Anyways, let's press on because we have so many great questions to answer. AI hard, here we go. So we defined NP hard as follows. A problem Q is defined to be NP hard if and only if there's an NP complete problem C that is polynomial time reducible to Q. So take an NP complete problem, do the reduction, and then we say, okay, it's NP hard. Do a similar thing as we did for the previous definitions, just change around a few words. We'll say that a problem Q is defined to be AI hard if and only if there's an AI complete problem C that is polynomial time reducible to Q. And I know the word time keeps on appearing, but just it's fine. We can kind of ignore it. It's just like a reduction is possible in like, and it doesn't take an extreme amount of effort. I know it's all subjective, but honestly, AGI is kind of subjective. And, we'll talk about that more a little bit later. But this is our definition of AI hard. Can we do the reduction? So, NP hard problems were at least as hard as NP complete problems. We'll have the same parallel here that AI hard problems are at least as hard as AI problems. And remember that if a problem falls in the set AI hard, it does not necessarily mean that it is an AI problem. Or equivalently, just because a problem is AI hard doesn't mean that it is human oracle solvable. So I believe examples are on the next slide. Here we go. Perfectly predicting the stock market. That is not human oracle solvable. It is not in the set of AI problems. It falls in AI hard, but just outside the scope of AI problems. Fully autonomous software engineering, where you have a technology that itself can diagnose what needs to be done and then come up with the code for it, and then diagnose the errors and make those fixes, and then fully develop a problem with essentially zero human input. We have something kind of similar, tools like Cursor, but fully autonomous with essentially zero human input. And protein folding, which I actually had a conversation with someone earlier today about it, and we were debating whether or not this is AI hard. So whatever, that's there. But yeah, Rob.
Wait, but for software engineering, like a human can software engineer, so why isn't that a AI problem?
I mean, maybe you could argue it is an AI problem. AI hard has some AI problems in it,
right.
But a lot of them are not AI problems. Maybe that is. Okay, so those are our classes. What's on the next slide? Here's the diagram again. And again, this completely parallels complexity. We had our set of AI problems. AI hard has some AI problems in it, but a lot of them aren't. AI complete are the cream of the crop, the hardest problems in the set of AI problems. Okay. We've defined classes. Now we need to populate the classes. I gave you examples of what's in AI complete, but let's go ahead and actually prove that we have an element in AI complete. So in complexity, we showed that SAT is an NP complete problem. This was the first NP complete problem that was found. by the Cook-Levin theorem. Do they still teach this in 2620? They do. Wow. Does anyone remember it? No? Yeah, I mean, that's a cool theorem, but it's, I don't know, it's pretty long and complex. But anyways, these two dudes proved that SAT is NP complete. It involves some sort of like Turing machine and the tape nonsense, and you move the tape thing. I don't remember that stuff.
So it like puts itself into the machine.
It
right?
does it?
Yeah.
Of course it does, right? Why not? But yeah, these two dudes did that, and I think what year was it? 72 is coming to mind, but that seems far too late. Can't be. No, because
68.
SAT stuff happened in the late 60s. Someone find it. Be interesting to know. And then once we proved SAT was a member of NP complete, we then leveraged SAT to prove that a bunch of other pumps were NP complete by doing the reductions, just like AJ mentioned. And so here we go. We're going to try to find the analog of SAT in AI complete world. We're going to find a problem, prove that it's AI complete, and then use that to solve a bunch of other problems. So then the question is, what problem do we look to? What is the almighty famous problem for this new world? SAT has so much clout because of its, relevancy in complexity theory. This should be pretty exciting. This is, we're finding a brand new SAT. Answer: Turing test. So we will show now that the Turing test is AI complete. And this proof is going to be so much simpler than Cook-Levin. It's also going to be pretty stupid, but whatever. So let's first define what the Turing test is.
Oh.
Here we go. The Turing test, according to this definition in this class, is a test of a machine's ability to exhibit intelligent behavior equivalent to that of a human. In the test, a human evaluator judges a text transcript of a natural language conversation between a human and a machine. The evaluator tries to identify the machine, and the machine passes if the evaluator cannot reliably tell them apart. This is copied and pasted from Wikipedia. Simpler definition. The Turing test involves a player P. And we will say that a player P passes the Turing test if P exhibits behavior equivalent to humans on some sort of test. And this is usually some sort of conversation that you have. And these two definitions look different, but they mean the same, right? Here, the evaluator is talking to a human and a machine, and the machine passes if the machine exhibits behavior equivalent to a human. So this purple definition is the same definition, just said a little bit more concise. So this is the Turing test problem. Something passes the Turing test if it behaves equivalently to a human. Well, what does that sound like?
Is there any limits on the machine, I guess? Is there any in terms of polynomial time frame? Because
No.
I feel like if this was just it seems like a broad definition, and say you have a machine that has a memorization of every possible human conversation.
Yes.
And then therefore it knows anything you say to it, it has a mapping of what's
right.
So
yeah,
that seems kind of arbitrary.
But that by definition that passes the Turing test. But such a machine doesn't exist.
So that would be
yes,
okay,
yeah. That would pass the Turing test. But okay, by this definition, something passes the Turing test if it exhibits behavior equivalent to a human. What does this sound like? Robbie? AGI, or basically, it can solve AI problems. It can do anything a human. It can solve human oracle solvable problems. And so, to prove that Turing test, or TT, great song by the way, is AI complete. We just stick to the definition of what it means to be an AI complete problem. First, we need to show that TT is an AI problem, and then we need to show that any other AI problem can be polynomial time reduced to TT. So let's do the proof. TT is an AI problem trivially. Why? I mean, we just kind of said it, right? Like, just by the definition of the Turing test. Like, if it passes it, then it can do things humans can do. And so, like, it's an AI problem, right? Okay. Number 1 is done. Now we need to do the hard part. We now need to show any AI problem can be reduced to Turing test. And this is where things start to get really sketchy really quickly. We're going to do it anyways. So, what this means is, like, we'll have this black box function called FTT. It's a function that we will say passes the Turing test, right? Because in this part, we're assuming that we have something that passes the Turing test, and we can use that to solve any other AI problem. That's kind of like the whole point of a reduction, or to show that this fact is true. So FTT is some player, some entity that passes the Turing test. And so our goal is to take any AI problem. Somehow, if we can give that to our Turing test machine, if we can give it to it, and if it can give us an answer to the AI problem, then we're in business, because we would have solved the AI problem using our Turing test machine. So this is the goal, to take any possible AI problem and use this as a tool to solve the AI problem, right? And the reduction is like this. You take the AI problem and you translate it to natural language. This is legitimately the entire reduction. Like, this is the reduction step, right? Yeah, Robbie.
How do you know that all AI problems can be converted to natural language?
Well, who knows? But we'll live with it for now, right? This is the vibe of the reduction right now. That happens to work for a lot of problems. Maybe you have to do a little bit more, but that's all we're gonna do. And I think I have an example. Let's see. Yeah, here we go. Well, actually, wait. Yeah, actually, no. This completes the proof, because we're we're taking any arbitrary AI problem. We are giving the problem to the Turing machine in natural language, and we are saying to the Turing machine, well, solve the problem, exhibit behavior equivalent to a human, and that gives us the answer to the AI problem. It almost feels as if Turing test is AGI, and I mean, Heike, it kind of is. But this completes the proof. We'll answer your questions later. But yeah, so congrats. We have proved Turing test is AI complete. Now that we've shown that it's AI complete, let's see if we can reduce a bunch of other problems to Turing test. And this is going to be even worse. This reduction is terrible. And yeah, I scrambled it together on the train. So let's see if it works. Here's a new problem, the image detection problem, where a player is presented with an image. Actually, it shouldn't be of an animal. Let's just say it's an image of something, and the player has to identify what's in the image, maybe with some sort of accompanying prompt. And it's basically, image, tell me what's in the image. We saw the cat, you could tell me it's a cat. So we're gonna prove that image detection is AI complete by doing what we need to do to show something's AI complete. First, we'll show it's in the set of AI problems, and then we'll show that Turing test reduced to image detection, just as we did with NP completeness, right? We showed SAT reduced to a bunch of stuff. So yeah, we already showed that image detection is in AI problems earlier, but just to further the point, I'm going to show you an image, and I'll give you some sort of prompt, and I want you to tell me what the image, or what the answer to the prompt is. So, what animal is this? A koala. Okay, great. What animal is this?
Hammerhead shark.
That's a hammerhead shark. What animal is this?
Duck.
My favorite animal, duck.
That's your favorite animal?
Yeah. And one more. What animal is this?
Toad.
Oh wait, it's that frog that digs in the sand.
Oh, interesting. I heard some frogs and some toads. This is a frog. But this is to show that the human oracle can solve it, right? That all minds put together. You know, the biologists and people who study frogs would know this, right? So we've shown that this is an AI problem, right? It's human oracle solvable, right? So that's step one. Now we're going to show that Turing test can be reduced to image detection. And so, what's the difference between these slides? Nothing. So maybe I give a question to my Turing test, my Turing machine, and I ask the question, what happens if I put a glass of water upside down on the table? Right? This is something I would expect my machine that passes the Turing test to correctly solve, right? Because it exhibits behavior equivalent to a human. A human reads this, and what's the answer to the question?
Spills.
It spills, right? So the thing that solves the Turing test should be able to solve it. And so we're going to perform the reduction and show that we can use image detection to solve the problem. And so our reduction is to take the question and turn it into an image, and maybe give it some sort of prompt, just as I did with you. And so this is our reduction. We've reduced the Turing test question into this input, and we're going to give this to image detection. And image detection will say spill if indeed this is like exhibits the AI complete properties. And that answers the Turing test question. And so we have completed the reduction. Yes.
Natural
So
language solver.
this reduction is saying, suppose we do have something that can solve image detection. Maybe you think of it like a proof by contradiction. Suppose this was like a polynomial time algorithm. Suppose we have a solution for this. If we can take something from Turing test and reduce it quickly into an answer for this, and it gives us an output, then we would have solved Turing test in like polynomial, or we've reached the desideratum for it.
I see.
Yeah, like we have solved all AI complete problems in a sense. Just like we did with SAT, like start with SAT, reduce it to the problem at hand. If we could solve that problem at hand in polynomial time, that would mean SAT is polynomial time. That's a contradiction. Therefore, SAT, or like that problem at hand, was NP complete. Here it's a similar thing. Suppose this is not AI complete, but if we can transform it into if we can transform Turing test, which we know to be AI complete, into something, that's a contradiction. Yeah. So that's pretty much it. Which is pretty disappointing because I feel like the climax of the lecture was in the middle, and the end gets like, what are we doing here? But this is in fact the AI theory and the different classes that you form. And so I guess the conclusion here is, well, we've defined these classes, and I don't remember how far back it was, but there's this slide where it's like, if everything holds, where is it? If all of these definitions hold, and if we show that the things are populated, then all we need to do, like we have now successfully defined all of the classes. We have shown AI complete is populated. We have shown that there's an equivalence between elements in AI complete. Furthermore, the quest for AGI just comes down to, can we have a machine that solves a single AI complete problem, which is far more digestible than do everything a human can do. And so before we wrap up, let's just do some other class-related stuff. So
I just have a question. Wait, so basically the idea is that if you can solve the Turing test, like the AI can like literally do anything.
yeah, pretty much. This Turing test sounds essentially like
Like they can make a
AGI.
building, or like they can play soccer, like
Yeah,
all
I mean,
physical and all like computational things. could be done by AI.
Right, because isn't the definition of Turing test that you interact with an entity and if it can perform equivalent to a human, it passes the Turing test?
But then like the thing is that
That's
like,
just AGI
there's,
though.
like when you're talking to someone, like the person can be stupid. So like it might sound like human, but then if they're stupid, like that means like and if
Say
AI
say
can pass
okay,
that-
instead of the communication with a human, communication with the human oracle, the collection
Okay.
of human minds. Yes. I know, I'm sorry. I wish that there was a more exciting conclusion to this lecture. I really do. I was really mad last night when I was like, wow, this is the worst way to end the last lecture, but here we go. Yeah. We've defined AI problems and the set of AI complete problems. We've shown that AI complete problems are equivalent. If we solve one, then we solve all of the others. So AGI comes down to just being able to solve one of these problems.